We're going to cover section 5.1 and hopefully 5.2 today. They're both about the same length in terms of slides, so hopefully we'll be able to get through them. So 5.1 is double integrals over rectangular regions. You can see your learning objectives there, and we have a nice definition that we're probably more than likely going to be using in the first example. So if you are someone who likes to take down the handwritten notes during class, or if you watch the YouTube or the video and the PDF later, you will want to write down 5.1 there. Okay. All right, so the first question is saying that we need to set up a double integral and approximate it by double sums. So we want to consider the function z equals fxy, which is 3x squared minus y over the rectangular region, and it's giving us a region between 0, 2 and 0, 2. So the first thing we want to do is we want to set up a double integral for finding the value of the signed volume of the solid S that lies above R and under the graph of F. So I believe we want to look at this image first. So this kind of gives you an idea of what we're looking at visually. I'm going to try to get parts A and B onto slide 2. Hopefully it will fit. If not, we might have to go to another slide, but that is the hope. So as we can tell from the given information, we have our given function and it is above the plane. To find the signed volume of S, we need to divide the region R into smaller rectangles, which is why you see the 4 regions in the image. Each area delta A and with sides delta X and Y, and we want to choose arbitrary points as sample points in each subregion. So the answer to part A really is just one line, and that would be that the volume is equal to the double integral over the region R dA. Okay, I guess technically if you wanted to make it 2 lines, you could. It's the limit mn as it approaches infinity. I hope I can fit this all in here. I'm sure you guys could have come up with that as well. 3. I'm going to go on the image a little bit. Okay. All right, so that is our answer for A. B says divide R into 4 squares with m equal to n equal to 2 and choose the sample point as the upper right corner of each square. So they did all of that for us. I'm sure you could have done the other corners, but you guys can play around with that if you would like. To approximate the signed volume of the solid S that lies above R and under the graph of F. So approximating the signed volume using the Riemann sum, we would have delta A, so this goes into part B. we would have delta A is equal to delta X times delta Y, which is going to be 1 times 1, which is just 1. So also, we know our sample points. These are our sample points. I'm not going to waste the space writing them. So because of that, we then would have volume equal to the summation. Wow, that was a terrible sum. And it's going to go from I equals 1 to 2 F of what you picked. I guess in a way what they picked. If you want to draw your little asterisks in, I'm not going to. Okay. So then we just have to plug in. So f of 1 times 1 plus f of 2 1 times 1 plus f of 1 2 times 1 plus f of 2 2 times 1 is going to give us 3 minus 1 times 2 plus 12 minus 1 times 1. Sorry, that's not a 2 there. That's a 1. I don't know where the 2 came from. And then 3 minus 2 times 1 plus 12 minus 2 times 1. Maybe that's what I saw the 2. And then when you clean that up, you're just going to get 2 plus 11 plus 1 plus 10, and that's going to give you 24. Okay. All right. So then we're going to do the last part, which is part C. Just divide R into the 4 squares and choose the sample point as the midpoint of each square. So 1/2, 1/2, 3 halves, 1/2, 1/2, 3 halves, and 3 halves, 3 halves to approximate the side volume. So we're essentially going to do it again. I'm not going to rewrite the every piece for you, but I will show you the fractional inputs. So you would have 3/4 minus 1/4 times 1 plus 27/4 minus 1/2 times 1 plus 3/4 minus 3 halves times 1 plus 27/4 minus 3 halves times 1. And then if you clean that up, you end up with 2/4 plus 25/4 plus a negative 3/4 plus 21 over 4, which will give you 45 over 4. And then what we want to take away from that is that it says, notice that the approximate answers differ due to the choices of the sample points. In either case, we are introducing some error because we are only using a few sample points. Thus, we need to investigate how we can achieve an accurate answer. Okay. So that is why, even though B and C sound like they should be the same, they are not. All right, what you're going to see next is that we have a few theorems. That is just really hard to find a great way to be on there right now. Just gonna let it be. All right. If you're having a hard time reading it, you can either read it in your textbook or you can wait for the PDF. Obviously, I would say care more about the intimate details here than all of the wording. But this is a very big theorem. And then we break it down into some definitions. So I'll let you guys do the writing right for a minute. Okay. All right. There are a lot of notes in this section, so that's kind of nice. And it looks like our longest example is the last one. Kind of. All right. All right. Again, for this one, you'll probably just want to wait for the PDF on some of it. But I like to pull the stuff out for you that I feel your textbook highlights, so that's just what we do. So we're going to use this. I'm super gonna butcher that, but I guess we'll go with Fabian's theorem. And we're gonna use that in our next example, because what you're gonna see is that using Fabian's theorem is an easier way to evaluate the double integral by using an integrated integral. So we want to note how the boundary values of the region R become the upper and lower limits of the integration. So I will show you how to work one of these. They're just giving us a very simple function of just x. So you want to start off all of these problems the same. So you should get some easy points right off the bat just in doing that. So then we're going to go from y equal to 0 to y equal to 1, and then x equal to 0 to x equal to 2, x dx dy. So then if we leave the outside one alone and we integrate, then we will do the same. So then the answer is just 2. Now, I wish they would have used the example we had before, but they didn't. So maybe they're building us up to it. All right. So for 5.3, it says illustrating properties 1 and 2. That goes back to this slide, I believe. So this is slide number 8, example, I believe it's 5.3. Okay. So this function has 2 pieces. You can see the first piece is xy and the second piece is 3xy squared. Also, the second piece has the constant 3. So we want to notice how we're going to use properties 1 and 2 to help evaluate the double integral. So first we'll start off by writing it out. And then you'll see off to the right, some of the steps. I'm not gonna like connect them. I just wanted you to have them off to the right. If you writing the steps down helps you, then go for it. So first thing we're gonna do is break it apart. And then we're going to go into our parts even further. We can actually pull this negative out if you would like at this point. And really, if you really wanted to, you could pull the 3 out, which I think I'm going to save us a little bit of time and lines. Yeah. So for a little bit, you're basically working them separately, and then at the very end, you'll pull it all together. So we want to do the first integral. So we're going to leave our outside ones alone. And you'll get x squared over 2, y 0 to 2 minus 3. X squared over 2, y squared 0 to 2, pi squeeze in my dy that I dropped there. And then we'll end up with uh, 2y dy minus so you want to pull your constants out. I'm going to try to do a couple of steps in one. Hopefully you can follow me because we're running out of room. So we're going to pull that out. We're going to do the integration. So then once you play around with it a little bit, you're going to end up seeing that some things cancel. So your 2's here cancel, and then your 3 reduces your 6 down to 2. So you end up with y squared 1 to 2 minus 2y cubed 1 to 2. So that gives you 4 minus 1 minus 2, 8 minus 1, which will give you 3 minus 2 times 7, which is 3 minus 14, so negative 11. All right, so that was using those first two properties. Okay, so let's see, this is example 5.4 on slide 9. Slide number 9, example 5.4 is going to use B. All right. I think we're doing pretty good on time. All right, so it says over the region R, we have the following. We have 2 to 13, and the expression is x squared plus y squared. Find the lower and upper bound of the integral that's given. So for a lower bound, we want to integrate the constant function 2 over the region R. For an upper bound, integrate the constant function 13 over the region R. So we're going to write it out. Of 1 to 2 and 1 to 3. You can see they're not doing the x's and y's anymore. You can leave them in if they make you feel better. I'm leaving them out purely for the sake of room. Oops. All right, so that's part of your answer. And then you would do the same thing, except we're going to do 13. So then your actual overall answer is going to be the following. See, nice examples that fit on one page. That's what we like to see. All right. This is 6 and slide 10. We'll go with black. So slide number 10, example 5.5. Okay, just in case you want to have that information when you're working on things. So we're looking at evaluating the integral, and we're dealing with e to the y cosine x over the following region. So this is a great example of this property because the function is clearly the product of two single variable functions, e to the y and cosine x. So therefore we can split the integral into two parts and then integrate each one as a single variable integration problem. So we will start where we always start, which is writing the problem. We're going 0 to 1 and 0 to pi over 2. E to the y cosine x dx dy. Oops. I have too many parentheses. And we would have e to the y 0 to 1. And then sine x 0 to pi over 2, which is going to just give us e minus 1. Alright. So we're gonna do another problem. We have a part A and a part B. I'm going to try to get them on the same slide. We might have to go onto the separate one, but I will do my best. Hopefully we can do like a part A here. I'm gonna move this up so you can see it later. We'll go with red and a part B there. So, we're going back to the function that we were given in example 5.1. So we're going to work this two different ways. The first way is we're going to integrate with respect to y and then with respect to x. And then we're going to flip it. Oh, sorry. We'll do with respect to x and then we'll do with respect to y. And you guys should see that it shouldn't make a difference. So it should be pretty easy. Now they do throw in the variables, probably because you're doing such a similar type problem here. I'm leaving them off, you can use them. We're gonna do all of A and then I'll do all of B. So 0 to 2. And I'm also skipping a little bit because I don't want to run out of space. So we're going to go ahead and actually do that integration. So then cancel. This time. So 9x squared minus 9 halves dx is going to be 3x cubed minus 9 halves x from 0 to 2. And if you throw that in, you're going to get a 15. All right, similarly, we're just going to switch up the spots. So again, I'm combining a couple steps, so I apologize, but I want to make sure we have the room. And again, you get 15. So the takeaway there should be that you get the same answer no matter what. I have to turn the light on real quick so you guys can go ahead and make sure you have all that down. All right. Almost done with the first section. Okay. So switching the order of the integration, consider the integral, the double integral x sine xy dA over the region. Express the double integral in two ways. So part A will actually have two answers. Part B says analyze whether evaluating the double integral in one way is easier than the other and why. And then part C says evaluate the actual integral. So, if you wanted, you kind of could do A and C together. I mean, it's kind of easy to do all of it together. So, obviously the first part A, what they're talking about is they're talking about the difference between if we're going to take with respect to X first or with respect to Y first. You still have to do both. So that is that idea. So, and that's literally all you would have to write for that kind of answer. You would just say, well, if we're going to go with Y first, then you would have your Y parameters first. And if you wanted to, you could write down integrate and then the other option would be to flip them. And you would just say integrate with respect to x first. Okay. As far as analyzing whether evaluating the double integral in one way would be easier than the other and why. So we want to consider if we want to integrate with respect to y first and then integrate with respect to x, you'll see that we can use a u substitution where u would equal xy, which would then give you du equals x dy. So I'll just kind of write this off the side. It's technically towards part B, but I'm just not ready to go there yet. So you want to consider that if we did with respect to x first, or sorry, y. Sorry. We would use let u equal xy, which would give you du equals x dy. Since the integral is simply the integration of sine u du, we can change the limits to be the functions of x. So let me go ahead to slide 13. I gave all of part B to slide 13. So if you continue on with that train of thought, so from slide 12, you would have had sine u du, which means you would have had the region x sine xy dA, and you would be doing 0 pi and then 1 2 x sine xy dy dx. And then if you use your integration, it would just be sine u du dx. Right? However, if we integrate with respect to x first and then with respect to y, then you have to use a much nastier looking option. So this would be x first. You would end up using a u substitution where you would have u equals x, which would give you a dv of sine xy dx. So then du is equal to dx, but then v is equal to negative cosine xy over y. So I think you guys can already see that it's going to get really gross, but I will just finish it out for you. So we have where we started. And then it's going to be 1 to 2, 0 to pi, x sine xy dx dy. equals 1 to 2. Very nasty looking option. Okay, so we're not gonna go any further than that, but you can see clearly why we would want the nicer option. So this would be Y first. Yay. All right, so you'll want to keep that in mind when you're going through your homework, when you're going through your test. Obviously, if it tells you you have to if you have to define both or you have to go through both methods, then obviously do so, but if you don't, then use the easier one. So parts C says evaluate the double integral using the easier way. So again, we're just going to start at the beginning. And we're going to choose to use going from X first. Although I will tell you, I believe their region is messed up. They've been using, in the solution at least, they've been using this. So I think that is how you should be writing it, not. I'm going to assume that they pulled that region from somewhere else, like from another problem. All right, so just so in case anyone goes back and is trying to figure out where we pulled that pi 0 to pi from. Oops. All right. So we're gonna go 0 to pi. And then we're gonna go u equals x, u equals 2x, sine u du, not a y. Very horrible square bracket, dx. And then that's 0 to pi, negative cosine u x 2x dx. Sorry, I'm writing into the spaces. And then 0 to pi minus cosine 2x plus cosine x dx. So that gives us negative 1/2 sine 2x plus sine x from 0 to pi. And if you plug that in, you're going to end up with a 0. Right. I have a definition that I can't get rid of this. Stop it. There we go. So you have a small definition there where it's giving you the area of a region of R is given by a R double integral over the region. 1dA. So we are going to do an area next. Right. Pretty close to being done with this section, and then we'll switch to the next one, which should be good because we're almost done now. All right, find the area using a double integral. So find the area. We know that area is going to be 0 to 2, 0 to 3, 1 dx dy, 0 to 2, 3 dy, pull the 3 out, 0 to 2 dy, it's going to be 3y, 0 to 2, and 3 times 2 is 6. Now, do I think that area problems are going to get harder than that? Absolutely. But that is the easiest part. Okay. All right. So 16 comes with a nice little visual. All right, so first notice the graph of the surface that we're asked to find and the above square region. However, we need the volume of the solid bounded by the paraboloid and the planes x equals 3 and y equals 3 and the 3 coordinate planes. Okay, so now let's take a look at the graph for the second part for B. Not for part B, but look at the second figure. We determine the volume by evaluating the double integral over the second region. And you would think this would be a big, long, crazy problem, but it's going to fit on here very nicely. So, volume is equal to the double integral z dA, which is the double integral over r 27 minus 2x squared minus y squared dA. And that's going to be 0 to 3 and 0 to 3. All right, 27 minus 2x squared minus y squared dx dy 0, 3, 27x minus 2/3 x cubed minus y squared x 0 to 3 dy. If you work out what you plug in, you end up getting 0 to 3, 63 minus 3y squared dy. So that'll be 63y minus y cubed, because the 3's cancel, 0 to 3. So you work that out and you get 162. If you need a little bit of extra notes here, we want to convert to integrated integral. And then integrate with respect to x. Okay, I'm sure you guys picked up on that, but it's there. Right. All right, go ahead and check out this definition and check out the weather map for a minute. It's going to help us with our next application-based example. All right. Last example for this section. All right, so we want to place the origin at the southwest corner of the map so that the values can be considered as being the first quadrant, and hence all are positive. Now divide the entire map into 6 rectangles. M equals 2 and N equals 3. As shown in figure 11. I'm going to show you that now. Don't know if I can leave it that big, but we'll try for it for now. Assume FXY denotes the storm rainfall in inches at a point approximately X miles to the east of the origin and Y miles to the north of the origin. Let R represent the entire area, 250 by 300. So that's going to be 75,000 miles squared. Then the area of each sub-rectangle is delta A equal to 1/6 75,000, which is 125. 12,500, sorry. Wow. Just want to keep making it a different number. 1, 2, 5, 0, 0. Done. All right. I'm not done with the problem, just done with writing that piece. All right, so we assume that our arbitrary points are approximately the midpoints of each sub-rectangle. Note the color-coded region at each of these points and estimate the rainfall. The rainfall at each of these points can be estimated as. I am not zooming in there. I'm going to write them out for you so you can have an idea, but I guess if you want to zoom in, you can. I'm just going to make a little list right here. So X11, Y11, the rainfall would be 0.08. X12, Y12, the rainfall is 0.08. X13, Y13, the rainfall is 0.01. X21, Y21, the rainfall is 1.70. X22, Y22, the rainfall is 1.74. And lastly, X23, Y23, the rainfall is 3. According to our definition, the average storm rainfall in the entire area during those 2 days. So we want to look for the average. So function average. It's not our favorite thing to do. Area R over the region fxy dx dy. You're going to have 1 over the 75,000 fxy dx dy. So going to try to do this in a way that you'll understand what's going on, but also not have to write all of these steps. So we're going to use what we just found for our average rainfalls. I'm going to bring them over. So it'll be the 1 over the 75,000 times all of our rainfalls that we just found. And then delta A. We know delta A is the 100 or the 12,500. So if we take the 1,000 or take the 12,500 divided by the 75,000, you're going to end up with 5 over 30. And then if we add the insides, I don't have my calculator. You can do it with me. 0.08 7 plus 3. Good get 6.61 times so you get approximately 1.1. So if you were to write it out as a statement, you would say during September 22 to 23, 2010, that date range, this area had an average storm rainfall approximately 1.10 inches. Okay. All right, so that is section 5.1.